Okay, this is the geometric series video. Like, geometric series, quick things, you're multiplying by a ratio each time. Okay, so your first term, let's take an example, 2, 4, 8, 16. Each time, in that the next thing in that sequence, you're timesing by 2. 3 formulas you need to know. There's not a secret formula this time that I didn't teach you in the lesson in class. So you've got un, which gives you the nth term, Sn, that gives you the sum of n terms. You've got this sum to infinity guy, and that only works under specific circumstances, so just be careful about that one. You can't use it all the time. And when we cover divergence and convergence in this video, you'll see when you can use it. Quick reminders: a is first term, n is your number of terms, and r is your common ratio, the thing you're multiplying by each time. I'm going to do an example, as I normally do, so if you've got your pack ready, that's what we're going to do. Then I'll show you the quick proof of Sn. Then I'll show you how to use sum to infinity. I'll try and keep this as brief as possible. Okay, so let's get ready and move on to that. Okay, so this time my chosen question is question 11 from exercise 3D. And the reason I picked it is because it shows a really, really important idea in geometric series. Merely that the common ratio is common, as in like, the common ratio you can find by dividing any two consecutive terms. So here we had a sequence that went k minus 6k and then 2k plus 5. So if you divide the second term by the first one, you get the common ratio. So here k over k minus 6. But you'd also get the exact same common ratio by dividing the third and the second term, so 2k plus 5 over k. And you can use that to set up equations, specifically quadratics in this case, and they love to kind of test you that way. If you want a numerical example, let's go back to 2, 4, 8. If you divided the second term 4 by the very first term 2, 4 divided by 2 is 2. And then if you had 8, which is the third term, divided by the second term, 8 divided by 4, again it's 2. Common ratio is 2. So any two consecutive terms can be divided, the larger one by the smaller one. When I say larger one, I mean the one that's the bigger term, the third term divided by the second term is what I mean. Or the 10th term divided by the 9th term, and it doesn't matter which two you choose, you will end up with the same ratio. The mathematics is relatively simple after that, but the key idea I really, really want to get across for part A of this question is that the common ratio really is common, and you can just use it for any two consecutive terms in a geometric series. The question is actually pretty easy. I mean, I'm not going to spend too much time talking about it, except for part D, which I'll put on in just a moment. So I'll just run through it quickly. I use the fact that these two were fractions, made them equal to each other, solved for k. Part B, I factorised the quadratic, got that k was 10. I mean, k equals minus 3 makes no sense in this context because the question literally says, if you look at it, positive constant. And then C, I worked out what the actual common ratio was by substituting numbers in. So you've got k equals over k minus 6. So you've got 10 minus 6 is 4. 10 over 4, 2.5. So that's that for A, B, and C. And I want to do D in a bit of detail so you can actually see a geometric series being done. Okay, so this is part D work through. A, and R are identified. A is 4. First term is 4. And the reason I know that is because obviously if you've got 10 minus 6, you've got 4. N is 10. They ask you for 10 terms. Ratio is 2.5. Plug it into the formula. That Rn probably should have a bracket on it. I do apologise for that. You see that it reappears in the second line. You plug in the numbers and you get your answer. I mean, it's not particularly difficult, right? I don't really think I need to spend too much more time on that, but it's just showing you that the formula works, it is applied, and if you check the answers, I've got that right. It is, by the way, rounded. I mean, I think it's 25,428.6 or something like that. But don't worry about that. I've got that to 5, literally 5 significant figures. That's good enough. Okay, I hope that doesn't seem too baffling to you. That's part D done of the question. What remains in this video, I'm going to quickly prove it to you that this A1 minus Rn over 1 minus R formula is a true thing. And then finally, I'm going to talk to you about being divergent and convergent. Let's move on. Okay, we have the proof here. Here's how it works. Sn is the sum of a geometric series, means that you've got first term will be your A, which is your starting term. Then you keep multiplying by R. So your first term after that will be AR. So like second term, AR. Third term, AR squared, because you've done A times R, and so on and so forth, till you get your nth term, ARn minus 1. Hopefully not too bad. Imagine you took that sequence that I've just described up there, and the addition of it, and times them all by R. Then your A would become AR, your AR would become AR squared, and so on and so forth, till the very last term, AR to the power n. Now, imagine you subtract the third one. And now here I was like, how would I know to do this? It's just the same as the arithmetic. It's a recipe. Follow it. RSN minus SN on the left-hand side, was if you're subtracting them. But then on the right-hand side, almost all of the terms cancel, except ARN and A. And that's why it's ARN minus A. Because if you're subtracting RSN from SN, all the AR squared, AR cubed, they'll all go. Factorize the SN on the left-hand side, factorize the A on the right-hand side, move the R minus 1, to the right-hand side, and you've got your formula. And you need a little kind of hand-waving thing I do is I say, well, they're both equivalent to each other. Rn minus 1, R minus 1, 1 minus Rn, 1 minus R. Why is that true? Because basically, if you swap both of them round, you basically turn them both negatives, or basically swap their sign. And if you swap both their signs and they both do turn negative, then negatives and negatives will cancel. Right? And if they're both positive, same thing. Does that make sense? One last thing, and that is going to be divergence. And then I'll be quiet and go to sleep. Okay, so here we go. We've got ourselves one last thing to do, and that is this convergence business and sum to infinity. So basically, you can use the sum to infinity if and only if modulus of R is less than 1. So that means it only works if the modulus of R is less than 1. And if that's so, your series is convergent. You don't need to stress too much about that. Now, I told you more than you need to know. So just remember, if you've got the modulus of R is less than 1, and you're adding up this whole thing, then it converges. So you've got 1, a half, a quarter is the example we're going to do. First term's 1, our ratio is a half. Shove those numbers into the formula, and you get that this whole sequence, if you add up infinitely many terms, you'd get 2. I hope that makes sense. I don't think that's going to be particularly difficult. All you've got to remember is that modulus of R is less than 1. For your geometric series, you add them all together, you will get something that will converge. If it's greater than 1, it won't converge, it will diverge. Don't worry too much about oscillating or anything like that for the time being. Let's just leave that as it is, and we'll call it a day here.